Greetings 347 fans. Another video on higher order differential equations, specifically in this video second order differential equations. We'll go ahead and have a look at a new flavor of a second order differential equation called a Cauchy Euler equation, and then we'll talk about a couple different methods for simplifying second order differential equations. They actually apply to higher order differential equations too, just so long as they're linear. So overview, more general form of a second order linear differential equation is given here, and again the key here is that this differential equation is linear in the unknown function and its derivatives, which in this case is x. The coefficient functions p and q can be anything they want. However, if they're constants, then we have the constant coefficient differential equation that we saw before. So this is a more general form of that second order linear differential equation. I do want to point out that that method we've developed to address the constant coefficient differential equation, namely trying a solution of the form e to the lambda t, does not apply to this more general differential equation. Okay. Nevertheless, when p, q, and f are continuous on some interval, there's an initial value problem that has a unique solution on that interval. The homogeneous differential equation, you can find a fundamental set of solutions, x1 and x2. And of course, the general solution to the non-homogeneous differential equation is the general solution of the homogeneous equation plus any particular solution. So all of that sort of solution structure from our study of constant coefficient second order differential equations, even when they're non-homogeneous, works here too. Okay, so let's talk about a certain flavor of these second order differential equations called Cauchy Euler equations. Start off with the definition. Definition: second order linear homogeneous differential equation x double prime plus b over t x prime plus c over t squared x equals 0 is called a Cauchy Euler equation. As you can imagine, we've got to avoid the point t equals 0. The coefficient functions are not continuous around t equals 0. Okay, and if you multiply through this equation by t squared, it makes it a little bit easier to handle. So multiply through by t squared, and you might notice that for every derivative you take, you add an additional power of t, right? So here you have this term cx squared, cx, you have a term bt x prime, and you have a term t squared x double prime. Okay, that sort of suggests something. That suggests maybe trying a solution of the form x to some power. You can imagine that power functions are functions that decrease by a power every time you take a derivative, and if you decrease by a power and then multiply by that power again, you'll end up with an expression you can mix up and maybe equal out to 0. Okay, so that's the motivation for trying a solution of the form t to the m. So to solve the associated homogeneous Cauchy Euler equation, when we defined our differential operator L as Lx equals t squared x double prime plus bt x prime plus cx, we'll try a solution of the form t to the m and just see what happens. Okay, so just like before, when we tried a solution, you need to calculate the derivatives of x to be able to plug those in. So of course we'll just apply the power rule here. If x is t to the m, the derivative is m times t to the m minus 1, and the second derivative is m times m minus 1 times t to the m minus 2. Now with these forms for the derivative and the second derivative as well as a function, it's pretty quick to see what Lx is. So of course Lx is given by t squared x double prime plus bt x prime plus cx, and when we plug those expressions for x and x double prime and x prime in here, right, we can see that we get something that actually simplifies to factor out a common factor of t to the m power. Okay, so there's this factor of t to the m power. When you go ahead and require that Lx equals 0, in other words, that x is a solution of the associated homogeneous equation, we see that t to the m is a solution of Lx equals 0 if there's some quadratic equation that's equal to 0. Okay, so this is a very familiar feeling for us, right? We've, again, reduced the question of solving a differential equation to the question of solving an algebraic equation. And just like before, This algebraic equation for a second order differential equation is a second order polynomial in M, which may have real distinct roots, it may have real repeated roots, and it may have complex conjugate roots. A little bit of terminology here. We call the trial solution t to the m for the homogeneous Cauchy Euler equation gives rise to what we refer to as the indicial equation. Okay, so this is the indicial equation, this quadratic in M, and if m is a root of the indicial equation, then t to the m is the solution of the differential equation. As you might imagine, just like before with our constant coefficient differential equation, although this one is different, we sort of gain the same intuition that each case gives rise to two linearly independent solutions. So if you have real distinct roots, here I'll call them m1 and m2. One solution is t to the m1 and the other solution is t to the m2, and lo and behold, those functions are linearly independent. So together they form a fundamental set of solutions. The second case, the case of real repeated roots, I misspoke. One solution is certainly t to the m, and it turns out that the second solution is t to the m times the natural log of t. Now, we'll verify this later, or we'll derive this later, but I invite you to go ahead and press pause and verify this now just by plugging that solution in to the differential equation in the case where m is a real repeated root. Okay, welcome back. Certainly those two functions are linearly independent, and the two functions together form a fundamental set of solutions for this case. The case of a complex conjugate root, similarly, you end up with two real valued solutions which are linearly independent by just examining one root, and those solutions are t to the alpha times the cosine of beta log t and t to the alpha times the sine of beta log t. Once again, you use Euler's identity to derive these two solutions. I won't go through that in gory detail, but it's pretty straightforward just by using exponentials and logarithms correctly. In any case, those functions are linearly independent, so we see that a fundamental set of solutions is given again by t to the alpha times cosine of beta log t and t to the alpha times sine of beta log t. Okay, so just to recap a little bit here, the trial solution t to the m for the homogeneous Cauchy Euler equation gives rise to the indicial equation, again a quadratic in M, and when m is a root of the indicial equation, t to the m is the solution of the associated differential equation. Okay, so of course in the case where we have real distinct roots, m1 and m2, t to the m1 and t to the m2 are linearly independent solutions, and the general solution is a linear combination of those linearly independent solutions. In the case of a real repeated root of m, the two solutions, and again we'll derive this later, but I invite you to verify it now, are t to the m and t to the m times log of t. So the general solution, again a linear combination of those linearly independent solutions, which I've written here in a factored form as c1 plus c2 log of t all times t to the m. Finally, the case of complex conjugate roots. In the case of complex conjugate roots, the fundamental set of solutions is given here, and the general solution is again a linear combination of those two linearly independent solutions, which we've written in factored form as c1 cosine beta log t plus c2 sine beta log t all times t to the alpha. Okay. So let's go ahead and, before we do that, I'll mention that just like before, the purely imaginary case gives rise to solutions with only cosine and sine. As you might expect, alpha equals 0 gives us that t to the alpha is 1, and this purely imaginary case follows directly from the case where we have complex conjugate roots. Okay, so a few examples to sort of explore these Cauchy Euler equations. Here's a perfectly good Cauchy Euler differential operator, and in this example we want to solve the associated homogeneous differential equation. So again, like we did before, we'll try a solution of the form t to the m. Of course, we need to be able to identify the action of the operator on our solution t to the m, so compute its first and second derivatives, and plug those into the differential operator, and we can see that we end up with the quadratic in m we have here all times t to the m power. Now, of course, our function is a solution if that expression is 0 for all time, which gives rise to a quadratic in M, right? So again, the indicial equation here tells us the roots that correspond to solutions of the form t to the m. Of course, this one factors nicely as m minus 1 quantity squared equals 0, so we can see that m equals 1 is a real repeated root. Okay, so when m equals 1 is a real repeated root, we know what the fundamental set of solutions is. A fundamental set of solutions is t and t times log of t, and of course a general solution, in this case we'll just work the general solution on the interval t greater than 0, turns out to be c1 plus c2 log of t all times t. So again, here I've written that expression in factored form, kind of for ease of transition. Now that being said, this is also a solution for t less than 0, but it turns out that it can't be a solution at 0. Of course, the solution isn't even continuous, much less twice differentiable around t equals 0. Okay, so usually these equations are solved for t greater than 0, and that's what we'll go ahead and do here as well. Okay, so here's the second differential equation. Solutions to the associated homogeneous differential equation Lx equals 0 for the differential operator t squared x double prime plus tx prime plus x, where, again, this is a Cauchy Euler differential operator. So recognizing the Cauchy Euler form, we'll go ahead and try a solution of the form t to the m. And when we try a solution of the form t to the m, this time we'll just go ahead and jump straight to the indicial equation. M times m minus 1 plus m minus plus 1 is equal to 0. Okay, so here we see that m squared plus 1 has to be 0, leading to purely imaginary roots plus or minus I. Okay, so again, a fundamental set of solutions in this case is cosine log of t and sine of log of t, and the general solution, again, on t greater than 0 is a linear combination of those linearly independent solutions. C1 cosine log t plus C2 sine log t. Okay, finally, one third example that incorporates an initial value problem. So here's an initial value problem, which the differential equation is a homogeneous Cauchy Euler operator. So here we'll try recognize that Cauchy Euler form, t squared x double prime minus 6tx prime plus 12x equals 0, and try a solution of the form t to the m. As you might imagine, that solution gives rise to this indicial equation m times m minus 1 minus 6m plus 12 is 0, that can be expanded and simplified into this quadratic in m, which factors nicely as m equals m minus 3 and m minus 4 times m minus 4 is 0. Okay, real distinct roots m equals 3 and m equals 4, for which a fundamental set of solutions turns out to be t cubed and t to the 4th. Okay, so once again here we're operating on the interval t greater than 0, but a perfectly good solution on that interval t greater than 0 turns out to be c1 t cubed plus c2 t to the 4th. Now what remains here is to pick c1 and c2 in order to satisfy the initial condition. So here we'll do that. X of 1 is 1 tells us that c1 plus c2 has to be 1, and x prime of 1 equals 0 tells us that 3c1 plus 4c2 has to be 0, which again gives us solution to the system, and that solution is c1 equals 4 and c2 equals minus 3. Okay, so here's the solution to the initial value problem. It's x of t equals 4t cubed minus 3t to the 4th. Okay, I think we'll quit there for now. This is part 1 of other methods for solving differential equations, namely having a look at Cauchy Euler equations, homogeneous Cauchy Euler equations. So we saw that with a Cauchy Euler equation, a solution of the form t to the m leads to a quadratic in m, for which roots of that quadratic correspond to solutions of the corresponding homogeneous Cauchy Euler equation. Next time in the video, we'll have a look at variation of parameters and reduction of order. Those are 2 methods for simplifying differential equations in order to better analyze them. Hope you enjoyed this video, and so long for now. We'll see you next time. Bye-bye.